All right, so we've talked about different types of charge already in our past videos, and we've talked about the attraction and repulsion effects. But now it's time for us to learn how to quantify them. And we'll be quantifying them by using the formula for electric force. So we've talked about gravitational force, we've talked about frictional forces, we've talked about lots of forces. This is a new one to add. The good news is you will probably never see in AP Physics 1 a combination that combines electric force with any other forces, except for maybe a comparison to gravity. And the reason why that comparison to gravity is going to come up is because the formula for the force of electricity, or this Coulombic force as it's called sometimes, should look really, really familiar. It's the force is K times Q1, Q2, all over r squared. And if that looks familiar to you, that's awesome, because that means you remember enough about what we learned about gravity to recognize that gravity had the same general format. The force of gravity, just as a reminder, was gm1 m2 over r squared. So the only thing that's really changed here is that we're talking about the charges, that's what the Q's represent, instead of the masses, and we have a different constant to work with. So let's go through this formula real quick and identify all of our variables. The first one to identify is, of course, we have the force itself, and that's going to be often just called the electrical force. But if you see it called the Coulombic force, don't be too surprised. And really, if you hear it called like the electrostatic or electromagnetic or something like that, those are all kind of terms that can be used more or less interchangeably. The next thing to talk about is this constant. This constant right here is called Coulomb's constant. Coulomb's constant. And it has a magnitude of 9 times 10 to the ninth Newton meter squared per Coulomb squared. So it's a big number, and that's important to recognize because the value for gravity, the force of gravity, was 1.6 times 10 to the negative 11th, I believe. I might be wrong on that. I'm brain farting right now, but that's probably about right. So notice that the electric force is actually way bigger. It's not 20 times bigger. It's a 1 with 20 zeros behind it. Bigger if we're leaving everything else kind of like compared to it, similarly compared. So it works out then that the force of electricity is actually very, very strong. And the reason why it's not a more dominant effect on your life, although it is actually pretty big, you just don't recognize it, is because it's hard to get those charges together in the same quantities that we can get mass together. Because mass is always an attractive force, we can get huge objects that then generate huge gravitational forces. If we tried to jam a ton of positive objects together and create like a positive planet with like a negative moon going around it, that positive planet would immediately explode because all of those positive charges would be pushing against each other. That's actually why nuclear reactions happen, is because once you add too many positive protons into the nucleus, they go, I'm out, you guys are lame, and then it explodes. Okay, so Coulomb's constant, 9 times 10 to the ninth. Then each one of these Q1s and Q2s represent our charges of each object. And the charges are always going to be measured in coulombs. So you might see something like 1 coulomb or 2 coulombs, but more likely you'll see something like 1 microcoulomb, which is equal to 1 times 10 to the negative 6th coulombs, or in the problem that we're about to do, 1 nanocoulomb, which is 1 times 10 to the negative 9th coulombs. We just don't see huge charges very often, especially not in the kind of theoretical problems that they throw at you. You can generate charges like 1 coulomb or 2 coulomb, but generally that's on something that's like big like a balloon, and then starting to measure some of the things like the R value starts getting a little bit weird. So that's stuff that we can talk about if you take AP Physics 2. So finally, this R value is really just going to be the distance. And just make sure that you're measuring it in meters. We have to do coulombs and meters in our calculations because our constant has meters and coulombs in it. If it had microcoulombs or nanocoulombs, if it had millimeters instead of meters, then we would use those units. But we have to match our units in our equation to our constants so that we get the right magnitude answer. All right, so there's the equation for Coulombic force. I'm going to go through some quick problems where I'm going to calculate the force on this object right there. That's always going to be this object down in the corner. So to figure out the force acting on that object, it actually is going to have two forces acting on it. And one of the forces is going to be from this 2 nanocoulomb charge. The other force is going to be from this positive 1 nanocoulomb charge. Now, something the equation doesn't do for us, and you have to learn to do on your own, is to determine the direction of the forces. We can calculate the magnitudes using that equation, but not the direction. So since this is negative and that's positive, this one is going to be an attractive force. So that's going to be pulling my negative 1 nanocoulomb towards the positive 2 nanocoulomb. And then this is a positive one up top, so the other force is also going to be attractive going upwards. So now I just need to calculate each one of these forces. Let's call this F1 and F2. F1 is just going to be equal to K, Q1, Q2 over R squared. Well, K is 9 times 10 to the ninth Newton meter squared per, over Coulomb squared. There's my K value. My Q value is going to be, it doesn't matter which one's which, we'll just go with 1 times 10 to the negative ninth coulombs. Instead of nanocoulombs, I'm turning these into coulombs. And then the other one is also 1 times 10 to the negative ninth coulombs. Notice that I didn't put the sign in here. I don't care about the signs. The signs are useful for me to tell what direction the forces are going. After that, I don't need them in my equation. So I'm figuring out whether this should be positive or negative or what direction it's going using a qualitative skill, not a quantitative equation. And then that's all going to be over R squared. And my R value is 5 centimeters, which is the same thing as 0.05 meters. So I'll put that in the bottom. I should have written meters in there. Oh well. So when we calculate that whole thing out, I'm going to look at my sheet because I don't want to have you guys watch me on a calculator. And I got 3.6 times 10 to the negative sixth newtons. Okay, so that's the force of attraction that exists here. There's one more force for me to look at. I have to figure out this force here. And I'm actually going to skip a lot of my steps now because the only thing that changed is one of these values doubled, which really means the only thing that's going to change is my total value will double. So I know that the force of attraction to the 2 nanocoulomb charge is 7.2 times 10 to the negative sixth. Now to find the total force of attraction, what I need to do is I need to do this with a Pythagorean triangle. I know that it's a force upwards of 3.6 times 10 to the negative sixth. It's a force over of 7.2 times 10 to the negative sixth. If I want to find the actual net force, I just need to find this value here, which is going to be 3.6 times 10 to the negative sixth squared plus 7.2 times 10 to the negative sixth squared. That whole thing square rooted. That will give me the value of C, my hypotenuse. And when I did this, I got 8.05, 8.05 times 10 to the negative sixth coulombs. Oh no, that's not good. So there we go. There's the work for that particular problem. If I want to figure out the direction, I can use a tan equation where I know I have right here this angle here. Tangent of theta is going to be equal to the opposite side. That's this side, the 7.2 times 10 to the negative sixth, over the adjacent side, 3.6 times 10 to the negative sixth. And my answer should come out to be, I did the opposite angle, so hold on, 90 minus 26.6, about 63.4. Okay. The other ones I'm not going to bother calculating because this video is going too long. So if you want to do them on your own, please feel free to practice. You'll get the same value. The only thing that's going to change is the direction of the force because everything else is the same. But let's talk real quick about the uncharged attraction. I talked about earlier how, like in a previous video, if you brought a balloon near a piece of paper that's totally uncharged, the piece of paper is attracted towards it. Well, the reason why that happens is because of the charge separation and the ability of uh, charges to conduct and move around a little bit within an object. So my piece of paper was originally uncharged. I had an equal number of positives and negatives. But when I bring like a positively charged balloon, sure, that's a balloon there. Oops. The positive charges are going to get pushed away because they don't want to be near the other positive charges. And the negative charges within that piece of paper are going to be attracted. And what's going to end up happening is I'm going to have two forces. I'm going to have the force of attraction between the positive and negative charges, and I'm going to have the force of repulsion between the two the sets of positive charges. Since the force of attraction is close, or those charges are closer, the electrical force will be a stronger attraction than the repulsion that is has a bigger R value will be pushing it away. So basically, FA will be bigger than FR, and so our net force is an attraction. So that's where that uncharged attraction is coming from. All right. Sorry these videos are going so long. I'll try and be faster in the next couple. Thanks for watching.